Howdy, howdy. Back we go. I'm going to kind of gather our thoughts here, make a sort of a large graph. I started one on the other page. I'll put another one here. So I have established an asymptote here and an asymptote here. I have established that the the x-intercept is here. You know what? I forgot to look at y-intercepts. Let's go back to that spot on that page right here. When we were looking at intercepts, the x-intercept, we let y equal 0 and solve for x. So over here on the side, let's look for y-intercepts. And you let y equal 0. I'm sorry, when you're looking for y-intercepts, you let x equal 0 and solve for y. But you can see that creates an impossibility. You can't divide by 0, so there are none. There is no y-intercept. So just take care of that loose end and go back here. And you can see also it makes no sense to have one because there's a vertical asymptote which is never crossed or touched. All right. So then we found also that it was increasing from 0 to 2. So if that's my 1, here's my 2. And I'm going to make my 1 very high on that axis. All right, so if from 0 to 2, we found out that it was increasing. So I'm going to indicate that just with some notes. So between 0 and 2, we're expecting it to increase. And the other segments, it was all decreasing. So from negative infinity to 0, it was decreasing. And from 2 to positive infinity, it was decreasing as well. So I'm just going to put some notes there so when I finally sketch the curve, it will obey those directives. All right, so now let's look at the max that we found. So the local max was 2 1/4. So this is a local max. So I'll remember that it's going to peak at that point. All right. So now I've sort of taken some notes, and what's left on our search is concavity and points of inflection. So let's work on that down here, and we'll go back up and put that data in. All right, so the first derivative ended up being, once I cleaned it all up, was 2 minus x over x cubed. So I grabbed that from a previous sheet. All right, so let's find the second derivative. Once again, I prefer to think of it as x to the minus 3 and use the product rule. Feel free to do it as a quotient. All right, so first times the derivative of the second. First times the derivative of the second plus the second times the derivative of the first. All right, clean it up, clean it up, clean it up. So let me write down what that equals. So I'll distribute the minus 3, and I get a 3x and a minus 6, and that is all going to be over x to the 4th. This one is a minus 1 over x cubed. So once again, as part of the cleanup process, it's helpful to give them like denominators. So multiplying this term by x over x, I get 3x minus 6 minus x over the common denominator, x to the 4th. All right. Are you following the algebra? I think I'm going slow enough that you can. All right, so for concavity, we're going to look for possible points of inflection and concavity by setting the second derivative equal to 0. X to the 4th. All right, so I notice the domain again. X cannot equal 0. So on my list of points, they don't call them critical points for the second derivative, but it's calculated similarly. So we have one point of interest, we'll call it, at 0, and we'll recall the second derivative does not exist there. Now, is there a place where this zeroes out? It zeroes out where the numerator is 0, and that is at 2x minus 6 equals 0, or x equals 3. So that is a point where it's a possible point of inflection. So I'm going to mark that on my little number line here. And that's where I put a 0, reminding myself that this is where it doesn't exist and this is where it zeroes out the second derivative. So I'm going to find points of inflection, we check the concavity on either side. So I'm going to test -1 here. And when I test -1, I put it into the second derivative right here. So it looks like I get a negative value. And between 0 and 3, I'm going to test 1. And then I get, looks like I get another negative value. All right, and then I'm going to test 4 between 3 and infinity, and that gives me a positive value. You can verify that for yourself at these test points. So therefore, there's not going to be a point of concavity here because the graph doesn't, the second derivative doesn't even exist there, or the graph. There's an asymptote there. So, but notice here the concavity does change at x equals 3 from negative to positive. So we found a point of concavity, and that point will be, not point of concavity, point of inflection, point where the concavity changes. So if I put 3 in the original function, which isn't even on this page, what is the original function? Y equals x minus 1 over x squared. So when I put in, well, for my x value, my 3, I'm going to get 3 minus 1, which is 2 over 3 squared, 9. We're going to get 2/9. All right, so having seen that was coming, I went ahead and made the graph kind of large. So 3 2/9 is the point of inflection. So I'm going to go down here and mark that. So 3 and 2/9. What was this point? 1/4. So 2/9 is going to be smaller. So I'll just mark it like right here. So that's my point of inflection. So we're going to have a smile turn to a frown. And that, nope, not a smile to a frown. We are going to have, if you look back down here at our little map, we're going to go from a frown to a smile. So we're expecting this kind of action around that point of inflection. So let's take some notes on that. So looking at these intervals, we had concave down from negative infinity to 0. So I'm going to add that to my notes. So in this section, we are expecting concave down. And then on the next section, if you recall, from 0 to 3. So I'm going to mark that on here. So all the way from here to here, this is 3, we're going to have also concave down. And then after that, our little map says concave up from 3 to infinity. So going back here, from here on out, we're going to have concave up. All right, can we put that together and get a sketch that is reasonable? All right, the original function, x minus 1 over x squared, let's give ourselves like a starting point in this area. So say like a number like 10. So we're going to be way down here somewhere on this axis. Not 10, but like negative 10. So if I put a negative 10 into this function, let's give myself a starting point. So negative 10 minus 1 is negative 11. So negative 11 over negative 10 squared gives me a negative 11 over 100. It's about a negative a tenth about. So it's going to start close here. And we notice that according to the calculus, it's going to decrease in this area and be concave downward. So it has to then go like this. Do you see how that's a decreasing function? If you were on a skis, you'd be decreasing, going downhill. And so concave down and decreasing, frowning and concave down. All right, so let's march across here. All right, so let's give ourselves if you recall, we have to cross this point. So recall that this is a 0, so it's going to come either like this or like this. But this data here will tell us which it is. It have to be increasing, so it can't come down like that. It's got to go up to be increasing, and at the same time be concave down, and then maximize right there. So do you see how these directives give us the graph? All right, so now we have a max. So what's going to happen after that? It's still concave down until we hit 3. So we're still frowning. And then at that point, it's going to change concavity and become concave up. So in that case, does it look like, oops, that's where I shouldn't use a pen like this. All right, so it was concave down, maxed right here. It remained concave down. This is still frowning. Then it has a point of inflection where it starts to smile. But because it is asymptotic to this line, it will get closer and closer to it. It won't bend back up, so ignore that little blip there. So here's the asymptote, it will obey. All right, so we've followed all the clues. Concave down, max, concave down, point of inflection, concave up. Can you see the frown started smiling? It's a very little smile, but it is a change in concavity, and it'll become asymptotic, always hugging and getting closer and closer to this horizontal asymptote. Remember, when you're near the origin, you are allowed to cross a horizontal asymptote. You may never touch or cross a vertical one, but close to the origin, the horizontal ones are not firm. So when you get away from the origin, they are. So that's how I knew it didn't bend back up. It actually hugged the x-axis. All right, hopefully yours looks a little neater than mine, but let me zoom out and show you the whole thing in its glory. All right, hopefully that will compute and you will be able to do something similar. I think they are long problems because you have so many aspects to look at, but just look at the packet we used to use just to come up with the zeros. So you can see, I think the calculus is going to help us get there more quickly and with less aggravation. All right, so chew on that and I'll see you tomorrow. Bye.